So we have this parametric relationship. We're asked to graph the curve. So it's a parametric relationship because the variable x and y are connected through the parameter t. Okay, so it's like there's a third variable that's in there. All you have to do to sketch a graph is to make a quick table of some values of t. Then you can plug it in, and then you can get the corresponding x and y values. Let's do the classic. If we plug in t equals 0, then we get x is 0. 2 times 0 is 0. Then we get y is 0. If we plug in t equals 1, then we get x equals 2 and y equals 8. And if we plug in t equals -1, then we get x is -2, and then we get y is -1 to the third is -1, -1 times 8, y is -8. So we got some points that are forming a graph, maybe one fraction. If we plug in t equals 1/2, then we get x is 1, and then we get y 1/2 to the third power. That's 1/2 times 1/2 times 1/2, right? So that's 1/8. 1/8 times 8 is 8. 1/8 times 8 is 1. Sorry. Okay, so the values of t, they're just, you can pick whatever values make the calculation easy so you can avoid fractions like that, because when we graph in the x and y grid, the t doesn't matter. The x and the y coordinate's the only thing that matters. So we got 0, 0, 2, 8. I'm not going to count out all those, so I'll just do 2, 8 right there. -2, -8 is a dot. And then 1, 1 is a dot. And then maybe we could get one more if you plug in -1/2. Then this is going to give you -1 for the x. And -1/2 over here, -1/2 cubed is -1/8. -1/8 times 8 is -1. So it's making that classic x to the third power graph like this, right? Okay, I think that's enough points. So we got a rough sketch of the graph. It shouldn't be a perfectly straight line though, okay? Should have a curve to it. So we got the graph. What are the initial and terminal points? That's determined by the values of t that your problem says. This says that t can be somewhere between -infinity and +infinity. That means t can be as small as you want or as large as you want. So there's no initial or terminal points. We'll see some problems where there are initial and terminal points. Find a Cartesian equation for the curve. So this is where we get to do some algebra. Look, if I solve for t here, I need to divide 2 from both sides, right? And what I'm doing is I'm using that substitution method from algebra. I'm going to plug in x divided by 2 in here for t. So I get y equals 8 times x divided by 2 to the third power. And I can do a little bit more algebra to simplify that. I can use the exponents rule. That's x to the third over 2 to the third. And so 2 to the third is 8. So 8 times something over 8 can cross cancel, right? And there we go. That was what our points were pointing to, that classic x cubed graph. So that's the Cartesian equation. You solve for t in one of the equations and then you plug it in the other. That's usually how you find the Cartesian equation for the curve. What portions of the graph the Cartesian equation is traced by the parameterized curve? Look, right now our findings were that every point of our graph of the parameterized equation was going to match up perfectly with what's going on here. That might not be the case when the functions start getting trickier, but right now there's no funny business. Our graph matches the y equals x cubed graph.